So we have Ryberg's equation here, which is E equal to a constant, which is a constant Bohr came up with to describe the energy related to a certain energy level within an atom, and that is divided by the energy level that electron is in. So N. N stands for energy level, and we'll continue to talk about that. That means energy level in our later examples. So this is sample exercise 7.4. And it's on page 300 in the book. And it says, first, calculate the energy required to excite the hydrogen electron from an energy level 1 to an energy level 2. So N equals 1 to an energy level of N equals 2. All right, so I want to calculate the energy, so I just have to plug this into the equation. These are my N values here, so I'll plug that into the equation for each of those. So E, energy of energy level 1 is equal to negative of 2.78 times 10 to the negative 18th. And that is joules. Sorry to put joules up there. That should be joules. Joules divided by 1 squared. When I do that, it should be pretty simple. That's negative. It just turns out to be the negative of that number. Negative 7.8 times 10 to the negative 18th, and that'll be in joules. And then I just do the same thing for energy level of 2. Plug that into my equation, so it'll be negative 2.178 times 10 to the negative 18th joules divided by 2 squared equals, when I do that, that gives me negative 5.445 times 10 to the negative 19th joules. All right, so in order for me, it says calculate the energy required. Okay, so I have to have an energy that, remember, an energy in the form of a wave that comes in to disrupt this electron. So I need to figure out the change in energy required. So I have a delta E. Delta means change here. So I want to subtract, so I'm going from an E2 or an E1 to E2, so anytime you're doing delta, you have to do delta equals final minus initial. All right, so my final is 2, my initial is 1. So now I just need to subtract these two numbers. So negative 5.445 times 10 to the negative 19th joules minus negative 2.178 times 10 to the negative 18th joules. So when I do that, my change in energy is 1.633. Change that, 633 times 10 to the negative 18th. So a very small amount of energy, but we're talking, in microscopic terms here. So 1.163, or sorry, 1.633 times 10 to the negative 18th. So then the question goes on to ask me in the next little sentence, it goes and asks me, where's my cursor? Okay, let's go to the next slide here. It goes and asks me, also calculate the wavelength of light that must be absorbed by the hydrogen atom in its ground state to reach this excited state. So I need to figure out the wavelength of light. So I know the energy of that. I know the energy of that light, but I need to know the wavelength. So I remember I have my equations here. I know from my first two light equations that energy is equal to hv. So h, remember, is Planck's constant, and I can rearrange that and plug in my v equals c, my speed of light constant, over wavelength, because I know, remember, the speed of light is equal to the wavelength times the frequency. All right, so eventually you get all this math and all this derivation, but I remember I want to end up with this equation here. Wavelength is equal to speed of light times Planck's constant divided by the energy. So we're going to solve for the wavelength. All right, so wavelength is equal to my constant, my Planck's constant, which is 6.626 times 10 to the negative 34th. That is joules, or joules times seconds. And I want to multiply that by my speed of light, which is 3.0 times 10 to the 8th meters per second. Then I want to divide that by my answer to the first one there, which was 1.633 times 10 to the negative 18th joules. All right, so let me change pen colors here. If I can do that. So eventually I do that. All my units here will show you my units will joules cancel out, seconds cancel out, and I'd be left in meters. All right, so my wavelength, once I do all this, would be equal to 1.216 times 10 to the negative 7th meters. All right, so that's the wavelength of light that I would need to absorb in order to displace an electron from the first energy level of hydrogen atom to a next energy level. All right, remember that's exactly the same wavelength that will be given off when that electron moves down from the second back to the first. And we call that an emission spectra, and we can see that when we see those different colors of light that we saw in the lab that were given off by different electrons.